Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is find the closest element in BST, and it is a medium level problem. So I don't think that it is a medium level problem because the core idea of the problem is very simple, straightforward. But still, I believe it's just because it is a binary search tree, it is a medium level problem, right? This is the only reason. Now they say that we have been given a binary search tree and an integer, and we have to find the least absolute difference between any node value of the BST and the given node integer. So let's say the integer is 13. Now we have to consider all the nodes, and among all the nodes we have to find the minimum difference. So for example, in this case the output is 2 and it is coming out to be because of this 11, right? Because 13 minus 11 would be 2, and that would be our best answer. If you try any other number, that would not give you a better result, right? So this is our whole problem, and the constraints are not specifically the constraints, but the expected and time complexity is the height of the BST, and the auxiliary space is the height of the BST as well. The total number of nodes are 10 to the power 6. So let's see how we can solve this particular problem. So we'll have a binary search tree like this, right? So this is a simple tree. Now we have been given some value k, and we have to find the minimum value of k minus node value. So node can be any node in the binary search tree, right? This is the minimum value that you have to find. So how do we actually go about finding this particular value? One way is to just traverse through all the nodes, right? If I go on this particular node, then this node, then this node, this node, this node, in any order you would like, right? And for all the nodes, you can calculate this particular value. So this will give me my final answer, and since the number of nodes are up to 10 to the power 6, so it is very well possible to traverse all the nodes, right? Then O of n. So this will be O of n. This will be the time complexity, and what will be the space complexity in this particular case? The space complexity will be log n, because in the recursion stack, the elements that we have here will be only up to the height of the binary tree. So if you are at this level, you have the first element pushed into the recursion stack. Now you make the next function call, so you go on to this level, then you make the next function call, so then you go to the next level, and one more thing is pushed into the recursion stack. So this way the overall space complexity will always be log n, but the time complexity becomes O of n. So how can we actually reduce this particular complexity? Now let's say this is a number line, and this is your current node value. So let me just write it at CV. So it is current value of the node. Now if k lies to the left of the current value, then it is always optimal to move this current value to the left. Why? So let's say the current difference between k and kV is like this, right? So let me just take the opposite so that it is positive. We are always taking the absolute value, so it doesn't matter, but in this way it will be easier to see a positive value like this. So the value will be CV minus k. Now if I take another number like this from the right side, so let's say new value NV, right? So NV minus k is always going to be greater than CV minus k, right? So this is very obvious from the number line. But if I don't take my new value from here, instead if I take a new value from somewhere here, so my new value is going to be always less than the previous value. Similarly, if k was not present on this side, if k was present on this side, I would obviously want to move my pointer to the right, right? I would obviously want to reduce the distance between k and the value, right? So this is my whole goal of the problem. So normally what I would do is, in a normal case, the first approach that I discussed, I would make the similar DFS call or traversal call to the left part as well as the right part, right? I am making the DFS call to both of the parts, and this way I will be visiting all the n nodes. So time complexity is O of n. But if I know which side I want to visit, then I will only consider that particular part. So either this will be called or this will be called. So at the end, you will only check log n elements. This is the maximum height of the tree. This is the maximum number of elements you can check. If you already know that you need to go in one direction, so you will never visit the other half of the tree, right? So we have discussed how do we determine which place to go. We will always try to move closer to the value k, right? And at each step, it is also important. At each step, you also have to update your answer as minimum of answer comma absolute difference of k minus current value. Why do we need to do this? For example, you were standing at current value and you don't know whether its children exists or not. If you are at the last node like this and there doesn't exist any children, you decided that okay, k is to the right, I would want to go to the right children, but later you discovered that there was no right children at all. So what in that case, you will always want to have your best answer updated as soon as possible. So like before calling this DFS or even after calling this DFS, you can just update your answer. So it is very important to do it every step, right? So let us have a look at the code now. So this particular approach will work in login, and as you can see, I have initialized my answer with _9, and I have a simple DFS function. I just call on the root. So this is my DFS function. What I am doing is, if the current is equals to null pointer, I just directly return, and I update my answer as minimum of answer comma absolute value of current data minus k, right? Otherwise, what I'll do is, if I know that my answer lies to the left, if my k value lies to the left, I'll call my DFS function to the left. Otherwise, I'll call my DFS function to the right, right? So this will work, and let me just quickly submit and show you that this works. So we see that it passes all the test cases and it is a valid approach. And let me just also show you the other approach that I was discussing. So this is also working, that it's like in this particular case, without checking, we are just making DFS call to both of the sides, right? So we are making the DFS call to the left, and we are making the DFS call to the right, right? And like both of the approaches are valid approaches. It's just that this particular approach will work in OFN, and the optimized approach will work in login. So I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to like, share this channel with your friends, and also subscribe to this channel. I see a lot of people who watch these videos have not subscribed yet. So if you're one of them, then consider subscribing. And till the next video drops, keep coding, stay safe, bye bye.